All right, let's get started. So today we're going to continue to quantitatively talk about solutions, and the focus of today is going to be several different ways in which we represent concentrations. It's coming, I promise. In chemistry, and actually all over the place. All right. So concentration, we're going to have several different units that we're going to learn. Some of them are used widely in chemistry, but almost nowhere else. Other ones are used in other fields more commonly. And we're going to learn a bunch of different types of units that we use for concentration. But importantly, they're all telling you the exact same thing. All right? Your concentration is simply a measure of the amount of solute in your solution. Now this might sound similar to what we were doing last class period when we were talking about solubility, except there was one important caveat where solubility was the maximum amount of solute that we could get to dissolve in solution. So that told you what the upper ceiling was, but of course we can always go lower than that. And we need to be able to accurately quantify how much stuff is floating around in there in our solution. So that's what our concentration is telling us. All right? So I'm going to leave this page here for definitions. I'm going to introduce them kind of one by one, but just sort of note that I'm going to kind of list all these definitions so that we have them together. Our first concentration, and the units that we really prefer in chemistry, but you will see nowhere outside of chemistry, is what's called molarity. All right, molarity uses this symbol capital M. Okay, and the definition of molarity is moles of solute per liter of solution. Okay, and you all are here because you survived Chem 1A, General Chemistry 1, right? And so you know how much we love talking in moles. That's how we bookkeep our chemical reactions. How much reactant gets converted to product. We have to do our stoichiometry, where these go-between units that we have to use are moles. So we love talking in moles in chemistry because it allows us to keep track of chemical reactions. All right? But there's a lot of other fields out there that need to keep track of concentrations, and they're not really concerned with chemical reactions. So this is a particular unit that's really unique to chemistry, and you don't usually see it too much outside of chemistry. All right? So again, I'm going to keep this page for a bunch of definitions. We're going to learn several different types of concentration units, but we're going to sort of introduce one and then practice it a bunch. Okay? So I'm going to go to a new page now. And this is where we're going to be practicing our molarity calculations. Okay? So what are all the things that I could ask you to do with the concentration that's in molarity, using that definition that we put forward here? All right, well, let's start most simply here. What is the concentration in molarity if we take 0.25 moles of NaCl and dissolve in 0.39 liters of solution? All right, we should be good with our verbiage. Into 3.9, or 0.39 rather, liters of solution. Okay, so how are we going to do this? We're going to use our simple definition here of what it means to be in units of molarity. We need to take moles of our solute and divide it by liters of solution. Okay, so my 0.25 moles of NaCl divided by my 0.39 liters of my solution. All right. Let me show you some notation that we use here. Since we're specifically talking about sodium chloride, whenever we're talking about concentration in units of molarity, we have this shorthand that we would use, which is this bracket notation. Bracket NaCl. This simply means the concentration of whatever inside the bracket, whatever chemical formula is inside the bracket, in this case NaCl, in molarity. All right, we're going to use this bracket shorthand quite a bit, and it stands for concentration of whatever it is your solute is, specifically in those chemistry units of molarity. So I'm going to punch this into my calculator here. 0.25 divided by 0.39. I get 0.641025. Just a bunch of extra digits. And my units here, moles divided by liters, does anything cancel out? No. So I'm left with those compound units of moles over liters. All right, which is the definition of that big M molarity. So you can either put moles over liters, or you could put that big M. They mean the exact same thing. All right, that's what the definition of that big M is. All right, and then lastly, what do I got to do here? I'm not quite done. Sig figs, right? So for a simple multiplication division calculation here, we're going to have to note these are both measurements. We have 2 sig figs in our moles, 2 sig figs in our liters. So final answer here for this concentration is 0.64 big M molarity. All right. Now this is just about the easiest molarity question that I could ask you. I'm just giving you moles, I'm giving you liters. You use that definition, plug in moles divided by liters, that gives you your concentration, right? Nothing too crazy, all right? It's also not a terribly practical problem to give you, because if you've ever been to the lab, there isn't a mole counting machine in there, right? Unfortunately, that doesn't really exist. So when we want to get if we want to take a certain amount of sodium chloride, we don't have a mole counting machine that will spit out 0.25 moles. Instead, we have a mass balance, and we go over and we mass out a specific amount of sodium chloride. And then we have to convert that into moles, all right? So a way more practical problem that I could give you would be something more along the lines of, what is the concentration in molarity? Right? When instead we're going to take 24.6 grams of NaCl into, we'll keep that same 0.39 liters of solution. Okay, so we're still going to need to use that definition of molarity, moles over liters, but first we're going to have to figure out how many moles of sodium chloride it is that we have. Okay, so we have, as always in a chemistry course, we have a periodic table. This is the periodic table that we're going to use in this course. It's embedded in all of your homework assignments. You can download it in probably 50 different places on Canvas under the introduction module of every chapter that we will be using it for. But even in a homework assignment that has it, that you're going to need it. It's embedded into that assignment, all right? But I'm making a big point of this because you have to use this particular periodic table, because the only thing that's different between one periodic table and the other, you can actually check up there, is not going to be the placement of the elements. Carbon is always right there, right? But the difference is the masses that are being reported are slightly different from periodic table to periodic table. So when we're using molar masses, we got to just standardize things in terms of what periodic table we're going to be using. This is the one that I've picked. This is the one that the course is built around, all right? So step one, we got to convert that 26.4 grams 24.6 rather, grams of NaCl into moles of NaCl using our periodic table here. All right, so I want everybody to take a second, remind yourself all the way from general chemistry, how do we convert from grams to moles for a compound like sodium chloride? We need that molar mass, absolutely, right? So we got our molar mass of one of those elements, sodium, and molar mass of the other element, chlorine. And since our formula here is 1 sodium and 1 chlorine, to get the molar mass of that compound, we're going to have to combine these together. All right, so I take that number from the periodic table. Well, that's not going to work. Take that number from the periodic table, the 22.989770 plus the 35.4527, and my calculator spits out, I'm going to put it over here for bookkeeping purposes, 58.44247. Now, I will say that creating a molar mass is technically an addition problem. So if I really wanted to be a pain in the butt, I would make you keep track of your sig figs with that addition. That's way too much work, all right? I'm going to cut you a deal. Just use every digit from this periodic table when you calculate your molar mass, and we can ignore the addition sig figs for calculating that molar mass. We'll just trust the number that our calculator spits out, okay? Now, importantly, what are the units on this molar mass? Grams per mole. And the way that I want you to do your compound units, you'll see it kind of more compactly written like this, and that's all well and good. But when we're doing like our dimensional analysis, where we're going to take this number and do more math with it, it's way helpful to have these split up as grams over 1 mole. Because then we get to just play the exact same game that we were playing all class period long, where we were just paying careful attention to our units, making sure everything canceled out, and then we knew it was all set up correctly, all right? We're going to see a lot of compound units, and it's going to be very helpful to split them up in this fraction form rather than leaving them all condensed like that. It just makes it easier to see how you're supposed to be setting up your problem. So for example, in this problem, I'm going to take this 24.6 grams of that NaCl, and I'm going to do what? Am I going to multiply by my molar mass as is, or am I going to have to flip it? I'm going to have to divide by that molar mass, or flip that fraction, right? And when we flip the fraction, we flip the entire thing. So not just the numerical value, not just the units, but I'm going to swap this whole thing. So I'm going to be multiplying by 1 mole and dividing by that 58.44247 grams. And again, the nice part being that I know that it's set up correctly, because grams will cancel out and leave me with units of moles of NaCl. All right, so punching this into my calculator here, I get 0.420926. Okay, and I'm just going to collect a bunch of extra digits after that sig fig. All right, so I don't have any sort of a rounding error. Even better, what I'm really going to do is copy the number on my calculator with all of those digits, all right? But even if you're doing this pencil and paper wise, you won't get any sort of a rounding error as long as you copy 3 digits after your sig fig. But remember, we don't want to round it right now, because we're going to take this number and do more math with it. All right, so now we have our moles of NaCl. We converted this. That was our 0.240926 moles of NaCl with our sig fig marked. And so now if we're looking for the concentration of NaCl in molarity, again using that bracket notation, I'm going to take my moles, divide it by my liters of solution. All right, I'm going to keep that sig fig marked so I can know for sure. I got a concentration of 1.07929. All right, my units are, again, nothing cancels out. I got moles over liters. I could write moles over liters or big M molarity. And then finally, when I'm going to do my sig figs, how many sig figs should my answer have? Just 2, right? So even though my moles had 3 sig figs, I'm limited by that denominator there, giving me just 2 sig figs, or a concentration of 1.1 molar. No, did I make a calculation here? 1.07 would round up to 1.1. You're good. It's very, look, if you do get something different than me, let me know, because the chances that I accidentally punched something into my calculator wrong or wrote something wrong are high, right? So I'd rather not confuse everybody if we do think that there was an error. So please just let me know. We always can double check. And I should double check and it should come out correct, right? So that's cool. Okay, cool. So practically speaking, calculating concentration with molarities, we just take moles divided by liters, all right? But again, I guess practically speaking part being that we don't have mole counting machines. So really when we go to the lab and we're going to measure out a certain amount of a substance, we take it to the balance and we mass that out, right? So we'd have to convert that mass to moles using our molar mass. Cool, so then how do we use our concentration of molarity? So this is calculating concentrations in molarity. How do we use these concentrations in molarity? All right, so let's say, how many moles of KBr are in 0.632 liters of a 2.5 molar solution of KBr. Okay, so first of all, what units should my answer be in when I'm all said and done here with this problem? Moles. How many moles of KBr, right? So that's what I'm looking for here, are moles of KBr. And I'm given the volume of this solution and its concentration. So how am I going to get to moles of KBr? So importantly, when you see a value in your problem, 2.5 molar, what we want to do is convert it into a conversion factor. Put it in this form that we can use in our math that's going to let us know if everything's set up correctly. So I'm going to take this here, and I'm going to convert it into one of those conversion factors, one of those ratios, using the definition of molarity, moles over liters. So this is telling me that there are 2.5 moles of, in this case specifically, potassium bromide, in 1 liter of solution. All right, so I'm given this in my problem, this nice little shorthand that we use, 2.5 big M, 2.5 molar. I'm going to convert that into one of those ratios, into one of those conversion factors that I can use in my math. Lets me know that everything's set up correctly. Okay, so again, separating out those complex units. Just to kind of note here, similar to what we were saying with those solubility factors that we built, every bit of uncertainty in this number is built into that 2.5. So even though there's this one digit down here, this 1 is treated as an exact number. All right, so I'm not going to be limited by my sig figs by that 1 liter. All the uncertainty is in that 2.5 molar. Okay, so then I'm going to take my 0.632 liters of solution, and I'm going to multiply. All right, do I take it as is, or am I going to have to flip it? As is, right? I want liters on the bottom, 1 liter, and my 2.5 moles on top. And I know that this is set up correctly because liters will cancel out, and I'll be left with how many moles are in that solution, or in that aliquot of solution. Okay. My calculator spits out 1.58. My units, as we established, liters cancel out, so I'm left with moles. You can say moles kBr if you want. Importantly, the units are moles. So it's not a bad idea to keep track of what it is that you're talking about, but specifically on your homework, when you're told to enter the units, you just need to give me moles, right? Those are the actual units of the problem here. And then lastly, everybody's favorite, sig figs. All right, we got 2 sig figs here. I'm limited by my concentration. So 1.6 moles of KBr. That's how much is in that 0.632 liters of solution. All right. It's also a good idea at this point to stop and take a step back and just do kind of a sanity check of the number that you got out on the other side. Does it really make sense? All right. If there are 2.5 moles in 1 liter and I have less than a liter, then I should have less than 2.5 moles, right? So making sure your values make sense when you're doing these calculations, kind of take a step back, can be really, really helpful. You know, what ends up happening is sometimes you get kind of lost in turning numbers into new numbers, and you're just trying to marching along and punching stuff into your calculator and writing stuff down, and you start things aren't making sense. And you can catch that if you kind of just take a step back, zoom out and be like, does that number make sense? All right? So just a good habit to get into. Okay, cool. So big thing here, and this is going to be the same game that we're going to play with all of these different definitions of these units that we're going to cover, is taking that unit, which is really a compound unit, and splitting it up into this conversion factor form here. All right, that's what we're going to do with all these different definitions of units that we're going to be given here, making sure that we take those concentrations and turn them into these conversion factors, these ratios, which are really going to help us convert from one set of units into the other, or vice versa. All right, so one more here. I want you guys to try to do this one on your own. How many liters of solution of a, let's say, 1. All right, and before you do any math, I just want you to read the problem carefully and do one of those sort of sanity check things here. Okay, if I have a 1.4 molar solution of sucrose and I need 2.6 moles, should I be having more than a liter or less than a liter in order to get that number of moles? More, because if there's 1.4 in just 1 liter and I need 2.6, I'm going to need more than 1 liter, right? So again, just kind of simple sanity check. What do you think the number is going to look like on the other side? Can save you some mistakes. right, so again, we're going to take that concentration that was given to us, that 1.4 molar, and we're going to convert it into something we can use in our math that has those units broken up, moles over liters, 1.4 moles over 1 liter. Since we're starting out with moles of sucrose, we're going to need to divide by this concentration, right? Flip that conversion factor so that moles cancel out, and we're left with units of liters. And then lastly, we're going to do our sig figs. So our final answer here is going to be 1.9 liters of that solution are required if we need those 2.6 moles. Okay? Cool. All right. So anyway, this game here is going to kind of be my little trick to you as to how to go about approaching these concentration problems. Each concentration has a definition that in some way, shape, or form is amount of solute over amount of solution, right? That's what a concentration is. So if we take that and we break it up into these two units, that will help us then use that as a conversion factor to jump from one to the other. All right, now, as you get really good at this, you can start to shortcut things, all right? But if you're at all having trouble, go back to that definition of molarity. Okay, so going back to our definitions page here, we have molarity, which is what chemists use 99.9% of the time. And then exactly 1% of the time, we use this other unit, molality, which if you've never heard of it, don't worry, because it's literally used in like one specific context, but we're going to talk about that specific context next class period, so we want to lay some groundwork here. All right, molality is symbol is fancy m, fancy little italicized lowercase m for molality. All right, and the definition of molality is again moles of solute. That's how you know chemists use it. But over kilograms of solvent. Not solution, but solvent. Okay? So, given what we discussed about molarity and how to take that unit and break it up using that definition to use it in a conversion factor, let's see if we can apply that to this situation with this new unit of molality that's nobody's ever heard of before. All right? How many moles of solute are in a 3.75 molal solution prepared with 4.63 kilograms of solvent? All right, so let's do this first part together here. First thing I'm going to do is take this 3.75 molal, and this is my concentration. So using that definition, I need to turn it into one of those conversion factors. All right, the definition of molal was moles of solute over kilograms of solvent. So when I'm given this specific amount, 3.75, that means that there are 3.75 moles of solute in 1 kilogram of solvent. All right, and so this is my conversion factor that I got for my concentration that I will use in my problem. I'm going to give you another minute to see if you can't finish this off. Correct number of sig figs, all that jazz. Given my units here, when I split it up, I got kilograms on the bottom, so I'm just going to leave it as is. I'm going to multiply that by that molality. Times my 3.75 moles of solute that are in that kilogram of solvent. Punch that into my calculator. 17.3625. And my units here, moles of solute. All right, being good in reporting this to the correct number of sig figs here, I would want to report to 3 sig figs. So 17.4 moles of solute are in those 4.63 kilograms solvent of that 3.75 molal solution. All right, so again, same trick that we used last time, where we took that concentration and converted it into one of those conversion factors using our definition of what it meant to be a molal. Cool. All right, so our next three are going to all fall under a particular umbrella called parts by mass. And whereas molarity and molality are very unique to a chemistry classroom, these are all the units that everybody else in the world uses. All right, so if you go to a hospital, for instance, you have to deliver a certain amount of drug to somebody based on, say, their body weight, right? Well, they don't talk in terms of molar because they don't care about moles in the hospital. So instead, they talk in these parts by mass, right? How many grams of aspirin should this particular patient need per gram body weight, something like that. So they use these units instead. If you go to your medicine cabinet and flip around any one of those bottles, you'll see a lot of percents on the back there. That's one of these parts by mass that they're talking about, right? So these units up here are very unique to chemistry because chemists love moles. Most people don't care about moles, and so instead they talk in terms of mass, just in terms of grams of solute. All right? And so our parts by mass are always going to have the same basic format here, where we take the mass of our solute divided by the mass of our solution. But depending on the unit, we're going to multiply by a different factor f. And this really depends on the context in which you're talking about this concentration. All right? Most of the time, what you'll see is what's called a percent by mass. Percent, usually it's actually just written as a percent sign. Sometimes if they're good, they'll put m over m to say mass over mass. All right? But that's when your factor of f is simply equal to 100. So you're taking a simple percentage of what percent your solution is solute by mass. All right? So we would call this a percent by mass. Our units are just that percentage sign or percent in parentheses m over m. All right? However, if you go specifically into like environmental science, they tend to be talking about concentrations that are very, very tiny small, okay? So like the amount of lead that you can tolerably have in drinking water is an incredibly small amount. That's really not good for you, all right? So instead, they use ppms, or parts per million. Where that factor of F is equal to, you guessed it, 1,000,000. Or if they're even talking about something crazy small, they would talk in ppbs, which is a part per billion. Where that factor of F is, what do we think? 1 billion, yeah. 10 to the 9. Okay, so all of these fall under this umbrella of parts by mass. A percent by mass is when we take grams of solute over grams solution, multiply by 100, simple percentage, all right? Or we could change that value of F if we're talking about really small quantities. Parts per million would be grams of solute over grams solution times 1,000,000. And parts per billion, grams of solute over grams solution times 1,000,000,000. All right? So let's use these definitions here. Okay. What is the concentration in percent m over m? When 14.5 grams of NaCl are dissolved into 53 grams solution. All right, so everybody take a second just using that percent m over m definition, figure out what percent mass this solution is of sodium chloride. All right, so my percent m over m is grams of solute. My 14.5 grams NaCl over that 53 grams of solution. And what would be my factor of F here for the percent m over m? Times 100. All right, so that would come out to 27.358. And we would say percent, M over M, that's our units. All right, but doing our sig figs, we would final answer here, 27% mass over mass. Okay. Mass of solute over mass solution times that factor of F, with which 4% is 100. All right, I want you to do another one here. Okay, you can do this one on your own. All right, we're going to make this solution where we're going to take 63.4 grams of glucose, and we're going to combine that together, dissolve it with 146.2 grams of water, and you are going to tell me what that percent M over M is for that solution. All right, so I try to be tricky here. I want to see who got it. So what is my mass of my solute? 63.4 grams of that glucose. And this is divided by the mass of my solution. What's the mass of my solution? Okay, yeah, so let's be careful here. Water is what? The solution? It's the solvent, right? So I need my mass of my solution, all right? So, and this is one of the nice things about how mass works. My grams of solute over grams solution times 100. Well, what is in my solution? What are those two parts? The solvent and the solute. So this is the same thing as grams of solute divided by grams of solute plus grams of solvent times 100. All right, where my solution is both my solute and my solvent combined. And give me a second. This is where mass is really nice, because that doesn't work with all other quantities. So for example, if you took a liter of water and you mixed it with a liter of ethanol, you would not get exactly 2 liters of solution. It would be pretty close, but it's not exact. But if you took 100 grams of water and 100 grams of ethanol, you would have exactly 200 grams of solution. Mass is perfectly additive, right, like that, right? So this works because I'm talking about grams of solution here, and a solution by definition includes solute and solvent. So the mass of solute and solvent would give me the total mass of that solution. What's up?
I noticed that with your wording for the first one, that says dissolved, and this one you say combined. But like in a real world scenario, if we were to dissolve that 14.5 grams of sodium chloride into that 53 gram solution, would you do the same thing?
No, because I use this term solution. So I was giving you the mass of, in that first problem, I was specifically giving you the mass of solution that was created, right? Whereas here I just said I mix this amount of this and this amount of this together, okay? So that just, the key word here was really the fact that I told you mass of solution up top, and here I just said mass of water, mass of solvent, all right? So what we got to do is we got to figure out that mass of our solution. We're going to take our 63.4 grams of our solute. We're going to combine it with our 146.2 grams of solvent. And that will give me a 209.6 grams of solution. Okay. In this case here, my sig fig is in that 10th place in both of my inputs, so it's going to be in the 10th place in my product here, or my sum. So I'll have 4 sig figs associated with that mass. And then I'm just going to use my definition here. I'm going to take that 63.4 grams of my solute, I think it was glucose, divided that by that 209.6 grams of solution, times 100. All right, 30.24809% M over M, or being good with my sig figs here, 30.2% M over M. All right. Can you ever have a solution that's more than 100% solute? Would I ever get a solution where my concentration in M over M is greater than 100%?
No.
Right? It doesn't work just based on the definition. Solute plus solvent, even if you didn't have any solute in there, or solvent in there, which wouldn't technically be a solution, that still caps you at a max of 100, right? So again, just kind of an easy sanity check that we can do when we're doing our calculations. If we ever get a number above 100%, that just doesn't make sense with what the definition is. Cool. All right. So now let's work on, so this is how we've been working on calculating these percent by masses. Now let's work on using those percent by masses, right? If I'm given a solution concentration, okay. So how many grams of solution in a 4.6% M over M solution? How many grams of a, whatever, that works. All right, contains 12.3 grams of solute. All right, so just like before, I'm given my concentration here, and our first step is going to be the same as we were doing before, where we want to turn this into a conversion factor, into something that we can use in our math here. All right, so I'm going to take that 4.6%, I'm going to take this and I'm going to convert it into one of those conversion factors where we split up those units. All right, now according to my definition here, what was in the numerator? That was grams of solute divided by grams of solution. All right, and according to this number, 4.6%, I have 4.6 grams of solute. But is that in 1 gram of solution? I mean, logically, does that even make sense? Can I have 1 gram of solution that contains 4.6 grams of solute? No. So this is going to be where this is a little bit different from these other ones. When we were doing molarity, all we did was say 2.5 moles over 1 liter. When we were doing molality, we did this 3.75 moles over 1 kilogram of solvent. But because of that factor F that we multiplied by, this is not how many grams are in 1 gram of solution. This is how many grams are in 100 grams of solution. All right, so when we play the same game here, the value that we're given is going to be divided by F, our factor, grams of solution here. And we'll play the same game with ppm in a second and convince ourselves that it's the same. But importantly, a 4.6% mass over mass solution means that there are 4.6 grams of solute in 100 grams of that solution. All right, so everybody just take a second, finish off this problem now. Got the punchline here. What's up?
Oh, and just like the other columns, the uncertainty would be the 4.6.
Correct, yes. This 100 is now treated as an exact number in this. All that uncertainty is in that 4.6. Yes, good question. All right, so now I'm going to take my 12.3 grams of my solute. Am I going to use my concentration as is, or am I going to have to flip it? I'm going to have to flip it. 4.6 grams of solute in 100 grams of our solution. All right, punch that into my calculator, 267.39 grams of solution, because my grams of solute have canceled out. And then doing my sig figs, yes, as was noted, this 100 here is exact. All that uncertainty, those 2 sig figs, are in that numerator. So my final answer here would be not 27, but 270 grams of solution. All right, don't forget we don't want to change the number here. That 2 has to stay in the hundreds place, that 7 in the tens place, et cetera, et cetera. Even though my 0 at the end here isn't significant, I'll have a decimal, so I know that 0 is not significant. Okay? But I don't want to say 27 grams, because 27 is a very different number than 270. Okay? All right, so little trick here. Maybe we should just make a special set aside in our notes here. All right, using parts by mass as conversion factors. All right, if I had X percent M over M, we said that would be X grams of solute into, what was it? 100 grams of solution. All right, so then you're going to take a second, do the same thing for me for ppm. If I had X ppm, how would I turn that into a conversion factor? Same thing, but what's my factor here? So again, it's now X grams of solutes, but over 1,000,000 grams of solution. All right, and if we just want to complete this off by doing our ppb here, X grams of solute over 1,000,000,000 grams of solution. All right, and so this should just give you a sense of just how small a ppm or a ppb is, right? The idea that you would have like, a 10 ppb solution, 10 grams of solute in 1,000,000,000 grams of solution. All right, but sometimes that's a very helpful quantity to use. So like the legal limit for arsenic in drinking water is around 10 parts per billion. Not very much arsenic at all needs to be in that drinking water for it to be terrible for you, right? So when we use these when we are measuring things that are so teeny tiny small in concentration, we would use these sets of units here. Again, the one that you're going to encounter most often, and especially if you go into any sort of like nursing or medical field, is as a percent, right? Where that factor is simply 100. For whatever reason, we love percents. We're just kind of trained of thinking of numbers as percents. All right. There's one more that we're going to add to our definition list here. And this is really because we're going to need to use it next class period. So we're going to kind of introduce it here today. This is what's called a mole fraction. Okay, this may sound familiar from last semester, specifically when you were talking about the ideal gas law and partial pressures. You would have been introduced to this idea of mole fraction. For mole fraction, we use this very fancy X. It's uppercase chi in the Greek alphabet. All right, and this stands for moles of solute over moles solute plus moles solvent. Full stop. No times 100 or anything like that. So it's very similar to a percent mass that we were talking about, but without that factor F. And importantly, you leaving things in units of moles. Okay, so just kind of to use it in the context that we were talking about before last semester, let's ask, what is the mole fraction of argon in a mixture of 2.45 moles argon and 3.6 moles of neon. All right, certainly not an aqueous solution, but still technically a solution, a homogeneous mixture of these two gases. And we can calculate the mole fraction of argon in that mixture. To be clear, this was a plus sign, even though it didn't look like it. According to my definition here, similar to what we were talking about with mass percents, what is the maximum value that a mole fraction could be? 1, all right? So we have moles solute divided by moles solute. So same thing in the numerator and denominator, plus this other part here. So the biggest value that you could ever get for a mole fraction by definition would be 1. All right, so again, just kind of nice sanity check. I also wanted to pick this one specifically because I've kind of been dodging difficult problems with regard to addition sig figs. And let's just review here how we do our addition sig figs once and for all. All right, we're going to put our numbers together. We basically go back to how we learned how to do addition in elementary school, where we line everything up at that decimal place. All right, so my 2.5 full moles of argon plus my 3.6 moles of neon. The rules for carrying sig figs with multiplication and division are about counting the sig figs of your inputs. But for addition and subtraction, it's about the position of those sig figs in your inputs. Right? So I would mark my last sig fig in each number. And the whole idea about carrying sig figs is we can't do an operation and get an answer that's more precise than what we started out with. Right? So my answer here is going to be limited in its precision to the 10th place. Whichever you mark the last sig fig in each number, whichever one is furthest to the left is where the sig fig in your answer is going to be. All right, so probably should have done this. All right, we get 6.05 moles total. But that number there only has those 2 significant figures, okay? So again, there's a video posted. I think everybody's pretty good on their multiplication, division sig figs. If you need the full review of addition, subtraction sig figs, they do come into play in some of our concentration problems, as well as some of our recrystallization problems. So definitely something that you guys want to have down. All right, but if you need that full review, there is a video posted under this chapter's module. All right. So here's our moles total. Let's finish this off. My mole fraction of, which one did I say? Argon is going to equal those 2.45 moles of argon over that total of 6.05 moles with my sig fig marked, so I know my answer should only have 2 significant figures. Okay, so punch this in. Again, I should get a number between 0 and 1. All right. The other thing that's kind of weird about mole fractions is these are unitless quantities. So we have no units. All right, those are fairly rare, but we will come across a few of them. Okay, so my mole fraction of argon is equal to 0.40, full stop, mole fractions. All right. Now, what if I wanted, instead, I was asking for the mole fraction of neon? I could definitely go through the same process of taking moles of neon divided by that total, or if I was going for the speed record, I would just note that all my mole fractions in a mixture have to add up to what? 1. They have to add up to 1, right? So my mole fraction of neon here would just be simply 1 minus that mole fraction of argon, our 0.60. Okay? All right, so just to be good, we're going to go note here, based on this definition that I gave you, this would technically be the mole fraction of what? The solute or the solvent in that mixture? So this would be the mole fraction of solute. All right, I could do the same thing to define the mole fraction of solvent, taking the moles of solvent divided by the total. All right, and this is actually going to be the helpful one when we're talking about vapor pressure next class period. So let's maybe just put it down here. Mole fraction of solvent is now moles of solvent over those total number of moles solute plus solvent. And of course, solute plus solvent, my mole fraction of solute plus my mole fraction of solvent should give me a value of 1, right? That's it. If not, I did something wrong. Cool. All right. This was today. All right, introducing you to all the concentration units that we're going to be using in this course. The one that we're really going to be doing just over and over and over again throughout the course, those units of molarity. But we do have uses for molality, mole fraction, and these parts by mass as well. Yeah. Nope. We're going to do exactly one topic that utilizes molality, and then we're going to do molarity for the entire rest of the semester.